All right, strap in, everyone. Today we're taking a deep dive into the discrete Fourier transform.
The DFT.
Yeah, DFT for short, if you want to sound cool.
Sounds pretty good to me. It's like you could say it's a secret decoder ring for signals.
Ooh, I like that.
Mm.
Secret decoder ring. Okay. We've got excerpts from the DFT's Wikipedia page, which can be pretty dense,
Definitely.
then a cool article on its history, which is always fun. So, what's our mission for this deep dive? What are we trying to do here?
I think our goal should be to demystify the DFT,
Okay.
like how it works, why it's such a big deal, and where you actually encounter it in everyday life.
Ooh, I like that.
You probably encounter it every day and just don't even know it.
Yeah, that's always fun. Okay, so just from what I've read so far, it seems like the DFT takes something really complex like music or, some kind of signal and breaks it down into all these little simpler pieces.
Yeah, kind of like separating all the instruments in an orchestra.
Oh, I like that. So it's like you can take the orchestra and then separate out like the violins and the violas and the cellos.
Right, and you can see how loud each one is playing at each moment in the music.
Okay, so if you put a sound through the DFT, you can see all the notes and how strong each one is.
Exactly. It lets us analyze the frequency content
Okay.
of any signal. It doesn't even have to be sound. It can be light or data.
Okay, so this all sounds pretty high tech. I mean, decoder ring, right? So where did it come from? Where'd this all start?
It actually started back in the 1800s.
Oh, wow. Really?
Yeah, with a physicist named Joseph Fourier.
Okay.
And he wasn't studying music or signal processing or anything like that.
Okay.
He was actually studying heat transfer.
Like if you have a hot cup of coffee and the heat goes into your hand.
Exactly. Imagine like a metal rod. You're trying to understand how the heat spreads through it.
I'm already getting flashbacks to high school physics, but go on.
Well, Fourier had this groundbreaking idea. He realized that that you could represent the temperature, like at any point along that rod, as a sum of symbol-sine and cosine waves.
Okay.
And these are the same waves we see in sound and light, like the most basic wave you can imagine.
I see. So he was basically saying that even really complex things, like how heat spreads can be built up from like simpler building blocks.
Exactly. And that's a really powerful idea.
Yeah.
Because once you break something down into those simple building blocks, then you can analyze them, understand them.
Right, like Lego blocks.
Exactly. And so Fourier's work kind of laid the foundation for what we now call Fourier analysis, which includes the DFT.
I see.
But there was a catch.
Okay.
Back then, actually calculating all these sums of waves, it was a computational nightmare.
Oh, yeah. I can imagine, like, hundreds of years ago trying to do all that math by hand.
Oh, absolutely. It was intractable.
No calculators, no computers.
It wasn't until like the mid-1960s that things really took off.
Oh, okay.
And that's when a couple of mathematicians, Cooley and Tukey, they developed the fast Fourier transform, or FFT, which is basically an algorithm for computing the DFT really, really quickly.
Okay, so it's like they found a shortcut that makes the DFT actually usable.
Exactly. It's like having a supercomputer in your pocket compared to what they had before.
I like that analogy. So they kind of unleashed the power of the DFT
Exactly.
by making it fast.
Yeah, and it's funny, actually, like a really famous mathematician named Gauss, he actually had a version of the FFT way back in 1805.
Wow.
But he never published it. He was studying asteroid orbits at the time.
That's incredible. Talk about being ahead of your time.
Right. And it really highlights how important efficient computation is for scientific breakthroughs.
Okay, so we know the DFT breaks down signals into simpler pieces. The FFT makes it fast. But how does it actually work? Like, if I were to give you a signal, what would you do with it?
Well, think back to that orchestra analogy. It's
Okay.
like you have this recording of the orchestra playing,
All right.
and you want to figure out how loud each instrument is playing at each moment. The DFT is like a magical filter that separates out each instrument so you can listen to them individually.
So if the orchestra is the signal, then the instruments are the frequencies.
Exactly. The DFT takes this complex signal and it pulls out all the individual frequency components, showing us how much of each frequency is present.
And the Wikipedia article, it even has a formula for it. Equation 1, I think.
Yeah, there's definitely a formula, but I don't think we need to get bogged down in all the math right now.
Okay.
The important thing is to grasp the concept. And the concept is the DFT takes a complex signal, right, like a sound wave, and it reveals its simple building blocks, which are sine waves of different frequencies.
So I don't need to be a math whiz to understand how the DFT works.
Not at all. We can appreciate its power just by focusing on what it does and not necessarily how it does it. And what it does is pretty amazing. The DFT has these unique properties that make it incredibly versatile.
Okay, like what?
Well, for one, it's linear. which basically means that if you combine signals, it's the same as combining their DFTs. So it's really easy to analyze systems that handle multiple signals at once, like your phone or a musical recording.
So if I understand correctly, linearity means you can take a really complex problem, break it into smaller chunks, analyze those chunks,
Right.
and then put it all back together.
Exactly. And that's a huge advantage for engineers and scientists who are dealing with really complicated systems.
Okay, that makes sense. Any other cool properties?
Yeah, there's also time reversal. So if you flip a signal in time, it flips its DFT in frequency.
It's like a time machine for your signal.
Yeah, you could think of it that way. And there's also this really interesting relationship between the real and imaginary parts of a signal and its DFT.
Wait, imaginary parts, what's that about?
Yeah, complex numbers.
Is this what you were talking about before?
Yeah, complex numbers are crucial for the DFT because they allow us to represent both the amplitude and phase of each frequency component. So the amplitude tells you how strong a frequency is, and the phase tells you where it is in its cycle.
Oh, okay. So it's like, is it at its peak or is it at its trough? Or is it somewhere in between?
Exactly.
All right, so complex numbers give us a lot more information than just real numbers.
But more.
Okay, that's starting to make a little bit more sense. But what about those basis vectors and orthogonality that the Wikipedia article mentions? Those sound a little scary.
They sound complicated, but they're actually really important for understanding how the DFT works at a fundamental level.
Okay.
Imagine you have a box of crayons,
Right.
and each crayon represents a different frequency.
Okay.
Those crayons are like our basis vectors.
I see.
They're all different.
Yeah.
And you can't create one crayon by mixing any of the other crayons.
Yeah.
And that's what we mean by orthogonality.
Okay.
Each frequency is unique.
Got it. So you can't like mix red and blue and get yellow
Exactly.
with frequencies.
Precisely. And because of this, we can perfectly reconstruct the original signal from its DFT. It's like knowing exactly which crayons were used to color a picture. You can recreate it perfectly.
Oh, okay, that makes sense. So each frequency component is unique. It adds its own special something to the overall signal.
Right.
What else makes the DFT so powerful?
Well, there's also the Plancherel and Parseval theorems.
Ooh, those sound fancy.
They sound complicated, but they express a very simple idea. So imagine you're listening to music.
Yep.
The music has a certain amount of energy.
Right.
These theorems basically say that the energy stays the same, whether you're looking at the music's waveform over time or if you analyze its frequencies with the DFT.
So it's like saying the total energy of the music is conserved, whether you experience it directly or you look at it through this mathematical lens.
Exactly. That's a really fundamental principle that underlies a lot of signal processing applications, like filtering or data compression.
Okay. Well, speaking of applications, this all sounds super cool in theory, but where does it actually show up in the real world? How does this affect my daily life?
Well, that's a conversation for part 2.
Ooh, a cliffhanger.
We've laid the groundwork. We know how the DFT works, but the fun part is seeing it in action.
I can't wait. All right, we'll be back in just a minute with part 2.
Okay, welcome back. I am ready to see the DFT in action. You promised some mind-blowing examples.
I did.
So let's see them.
All right, you got it. Remember how in part 1 we talked about that DFT formula
Yeah.
that takes a bunch of data points and it gives you back these complex numbers that represent the frequencies of the signal?
Okay.
Well, the Wikipedia article, it actually has this really simple example that illustrates this whole process.
Okay, I'm listening.
So it starts with this like super basic audio signal, and it only has 4 samples.
4 samples.
4 samples. They're 1.5, minus 0.5, and minus 1.
Okay.
And you can think of these as like snapshots of a sound wave taken at 4 equally spaced moments in time. So we're really zooming in on this sound.
Exactly, yeah. And so what we do is we take those 4 samples and we plug them into that equation 1 for the Wikipedia page.
The one with all the
all the scary symbols.
Yeah. Complex numbers still make me a little nervous.
Understandable. Basically, these complex numbers, they have 2 parts, right? They have a real part and an imaginary part.
Okay.
And they're super useful for representing things that have like a magnitude and a direction.
Okay.
So think of it like this. The real part tells you how strong a frequency is.
Okay.
And the imaginary part tells you where it is in its cycle.
So it's more complete information
Exactly.
than just having a single number.
Exactly. It gives you like 2 dimensions of information.
Okay, that makes sense.
And so when we take these 4 samples and we plug them into this DFT formula,
Right.
what we get back is another set of 4 numbers.
Okay.
But these are complex numbers now. And these tell us the amplitudes and phases of the different frequency components that are present in our original signal.
So each of those complex numbers represents a different frequency.
You got it. Okay.
And from those complex numbers, we can actually calculate what's called the magnitude spectrum,
Okay.
which basically tells us, like, how much energy there is at each frequency.
So if we were looking at like a visual representation of this,
Yeah.
it'd be like, how bright is each color in the spectrum?
Exactly, yeah. It's like looking at a rainbow and seeing, which colors are the brightest.
Okay, so what does that look like for this example, for this 4-sample example?
Well, if you actually calculate the DFT, the output that you get for these 4 samples is 0, 1.5, 1.5J,
Okay.
1 and 1.5, 0.5J.
Okay, so those are the
Those are the 4 complex numbers.
frequency components.
Right. Where J is just, how mathematicians write the imaginary unit.
Oh, okay.
It's, just a mathematical notation.
Okay. And then what are their magnitudes?
So for the first complex number, which is just 0.
Yeah.
The magnitude is obviously 0.
Right.
For the second complex number, 1.5J,
Okay.
that has a magnitude of about 2.12.
Okay.
For the third one, which is just 1,
Right.
the magnitude is 1. And finally, for the fourth one, 1.50.5J, that has a magnitude of roughly 1.58.
So what does that tell us?
Well, what that means is that the second frequency
Okay.
is the strongest, the most dominant,
Okay.
and then, next comes the fourth frequency.
Okay.
And then the first one is basically non-existent because it has a magnitude of 0.
So even with just these 4 simple samples,
Yeah.
we're able to get this information about, like, the relative strengths of these different frequencies?
Exactly. You can see which frequencies are more prominent
Yeah.
in the signal.
Okay, cool. So I'm starting to get how this works, but you said this has real-world applications.
Yeah. Help me connect the dots here.
Okay, yeah.
Wait, how does this apply to my daily life?
So it's actually all around you. It's just you don't really see it.
But let's think about, like, social media.
Yeah.
Every time you upload a photo to, like, Instagram or Facebook,
Yeah.
the DFT is being used behind the scenes to compress that image.
Oh, wow.
And this is what makes the file size smaller.
So it uploads faster.
Exactly.
And takes up less space on their servers.
Exactly. So every time you post a selfie, you're unknowingly using the DFT.
That's amazing. I had no idea. What about, like, music?
Music too, yeah.
Okay.
Like Spotify or Apple Music.
Uh-huh.
When they recommend you new artists or songs,
Right.
they're using the DFT to analyze your listening habits.
So they're, like, breaking down all the music I listen to into its frequencies.
Exactly.
And then finding other music that has similar frequencies.
Exactly. And that's how they find, like, similarities and patterns.
So it's like they have a mathematical sense of musical taste.
Yeah, pretty much.
Okay. What about in, like, music production?
Oh, yeah, definitely. Music production, like, all the time.
Okay.
It's used in tools for things like equalization and mastering, adjusting the balance between different frequencies in a track.
So it's like a super precise way to edit sound.
Exactly. You can make it sound clearer, punchier, warmer.
Okay, so that's music, that's media.
Yeah, that's just the tip of the iceberg.
You mentioned medical imaging before. Can you tell me more about that?
Yeah, so the DFT is actually crucial in technologies like MRI,
MRI.
which, doctors use to get these detailed images of your organs and tissues.
Right.
And it works by using magnetic fields and radio waves to
Okay.
create those images. And guess what? The DFT is used to process the signals.
From the MRI machine.
Yeah, to actually turn them into those images that the doctors use to make diagnoses.
So the DFT is helping doctors see inside the human body.
It is amazing.
That's incredible. Are there any other medical applications?
Oh, yeah, tons.
Okay.
Like EKGs, electrocardiograms, to measure your heart's electrical activity.
Right.
The DFT helps doctors detect heart problems and abnormalities.
Oh.
And it's even used in analyzing brain waves, the electrical signals from your brain. This can help diagnose things like sleep disorders, epilepsy,
Okay.
lots of different neurological conditions.
Okay, so the DFT is everywhere in medicine.
Pretty much, yeah. And we haven't even talked about telecommunications, radar systems, scientific research.
Oh my goodness.
It's everywhere.
Okay, I'm officially mind blown.
Yeah, it's really a remarkable tool.
But I'm also realizing how little I knew about it before.
Yeah, it's kind of a hidden force.
Yeah, this hidden force shaping our world.
Exactly, and that's what makes it so fascinating to me.
Well, I'm ready to dive even deeper.
Okay.
What else can we uncover about this amazing tool?
Well, in part 3, we're going to look at some even more specific and mind-blowing examples of the DFT in action.
All right, I cannot wait. Back in a minute with part 3. Welcome back to our deep dive on the DFT. You left me hanging in part 2.
Did I?
Yeah, you said there were more mind-blowing applications.
Oh, yeah.
So I'm all ears.
Okay, get ready, because we're about to see how the DFT is like the unsung hero behind so many things we just like take for granted every day.
Okay.
Let's start with your smartphone.
My smartphone. Okay, what does the DFT have to do with my phone?
Well, think about how you can make calls and send text and browse the web all wirelessly.
Right. Through the magic of the internet?
It's all thanks to radio waves,
Okay.
which are a type of electromagnetic wave.
Right. And those waves, they carry information.
Yeah, like the sound of your voice or data from a website.
Right. Exactly.
But to send these like really complex signals over radio waves, you need a way to encode them efficiently.
Okay.
And that's where the DFT comes in. It's used in a process called modulation,
A modulation.
where the information signal is combined with what's called a carrier wave,
Okay.
which is basically just a pure sine wave at a specific frequency.
So the DFT helps prepare the signal for its journey through the airwaves.
Exactly. And on the other end, your phone uses the DFT again
Okay.
in a process called demodulation. And that separates the information signal from the carrier wave.
Yeah.
And that allows you to, hear the other person's voice or see the website that you're browsing.
So it's like the DFT is the language translator that's
Right.
allowing all these different devices to communicate wirelessly.
That's a great way to put it.
Yeah.
Yeah, it's the reason we can even have wireless communication in the first place.
Wow, I never realized how much I was relying on the DFT just to use my phone. What about other wireless technologies?
Pretty much all of them. Wi-Fi, Bluetooth, GPS,
Okay.
even satellite communication, to watch live TV, make international calls.
Right.
All depends on the DFT.
It's incredible how something that sounds so abstract, the DFT, is actually at the heart of so much of our world.
Yeah, it really is everywhere.
And it's not just for communication, right?
No, not at all. It's also a big deal in scientific research.
Okay.
So, for instance, like in astronomy,
Okay.
scientists use the DFT to analyze the light coming from distant stars and galaxies.
Oh, wow. I've always been fascinated by astronomy. How does the DFT help us understand the universe?
So, when astronomers look at a star, they're not just seeing like a dot of light.
Right.
They're actually collecting a spectrum of light,
Uh-huh.
which contains all sorts of information about that star,
Like what?
like its chemical composition, its temperature,
Okay.
even its movement. And the DFT helps us to like break down this spectrum
Okay.
and reveal the different frequencies of light that are present.
So it's like a cosmic fingerprint revealing the secrets of the star.
Exactly. And it's not just stars.
Yep.
It's galaxies, nebulae, black holes, you name it.
Okay.
It's a really powerful tool for unlocking the mysteries of the universe.
I'm starting to feel like the DFT is like the key to understanding like almost anything.
It's definitely a powerful tool, yeah.
It's got to have some limitations, right?
Of course, every tool has its limits.
Mm-hmm.
Like, it's best for signals that are stationary, meaning that,
They don't change too quickly.
yeah, they don't change much over time.
Okay, that makes sense.
For signals that change rapidly or have, like, abrupt transitions, other techniques might be a better choice.
So it's important to use the right tool for the job.
Exactly.
Okay, well, before we wrap up, what does the future hold for the DFT? Where do we go from here?
Oh, that's a great question. I think as our computational power keeps increasing, we can expect like way more creative and innovative applications of the DFT.
Okay.
Researchers are like constantly developing new algorithms, new techniques
Right.
that leverage its power. Like it could be huge for artificial intelligence,
Yeah, oh yeah, that
helping
would be...
machines to process and understand really complex data, or even in quantum computing.
Oh, wow.
It's a whole new field that has like the potential to solve problems that are impossible for us right now.
So the future of the DFT is as bright as the stars. It helps us understand.
I like that. I think that's a great way to put it. Yeah, the possibilities really are endless.
Well, I think this deep dive has been incredible. I've learned so much.
Good. I'm glad to hear it.
Any final thoughts for our listeners? Anything you want to leave them with?
Just remember this. The DFT, while it comes from math, it's not just some abstract concept. It actually shapes our world in really profound ways.
Yeah.
From the technology that we rely on to the scientific discoveries that push the boundaries of human knowledge. So the next time you listen to music or watch a video or hear about a new breakthrough in medicine or astronomy, remember the DFT.
It's everywhere.
It really is. It's the silent force behind so much of what we experience.
Well, thank you so much for taking us on this journey. It's been a real pleasure.
It was my pleasure too. Keep exploring, stay curious,